trans. So we'll see. We'll see what happens there.
Ellie, if you want, I can record too.
Oh, it's okay. This time I'm recording so that it outputs the file in RAW, so that it doesn't it doesn't have to transcode it. I can do that.
Okay. Okay.
So, all right. So let me share. Oops, not share, slideshow. All right, so can you guys see my screen? It's okay.
Good.
Yeah.
Okay, so welcome to week 8, which is actually week 9, but we're really calling this 7.5. Because we'll talk a little bit more about the packaging and the monoids as review. And then we'll talk a little bit about functors, or things that lead up to functors, and then why you'd actually want to use a functor. All right, so anybody drinking coffee today? I finished my Starbucks coffee. I don't know if I call that coffee, but it's something. Anybody else have coffee?
No, I am eating an pineapple because I hate the coffee.
All right, so no coffee, no coffee. All right, so before 2 weeks ago, how were we limited? We could create programs, right, in a file or two, and maybe import into our file from our other file. It was pretty limited. So we had that, single depth structure. We only had, like, we could deal with importing from our same directory. And, we didn't know how to, like, import from another package. We didn't know how to import from say some other files in another directory. All this stuff was really not covered, and so we really didn't have very robust programs. We had pretty simple programs. And so there's a limit to how much you can program with simple structures, in that, like, what if you really wanted graphical user interface, or a terminal user interface, or a web server to do something? You couldn't do that with how we had it 2 weeks ago. You were just limited to, okay, say you create a module in one file and you import that module, and then you might use some of the core modules, like the data module, or the type classes from some other module that's core to GHC, and so it was pretty simple. And then after 2 weeks ago, so 2 weeks ago, what did we learn? We learned that there's this Nix package manager, either the Nix OS or the Nix package manager by itself. Remember, Nix OS really isn't an operating system. It's just basically like an operating system that's built around a package manager. And so you would set up a base set of packages that you need to run your system on. And if you were running it as just the package manager on your already existing operating system, it would just need to install whatever you said were your core packages that you needed for, say, your Haskell programs, or your say you were doing something else in another programming language, you could just set the environment up for those particular packages that were necessary. But Nix has a long-standing relationship with Haskell, in that a lot of Haskell programmers who use Haskell for major productions, projects, or whatever, will use Nix as the base, because Nix can say, hey, I want this particular version of this particular library available for Haskell to use, and we'll set it up as the base for our system. And so I don't really always recommend using Nix, but if you're going to be creating a large package with a lot of dependencies that need to be a specific version, using Nix is pretty helpful, because it can really install a lot of binary packages that are set up just for your system, rather than having to compile them from scratch, or having to use your own package manager. Say you're on Mac OS and you have to use Brew, or you're on Ubuntu and you have to use apt-get in order to get the dependencies set up. It's a little harder than if you're using Nix. But for simple packages where you only have like 1 or 2 dependencies, or 1 or 2 major dependencies, and that those packages will install other dependencies, then you may not really need Nix. But Nix is there just as a resource for how to make sure that your system can be set up with all the dependencies it needs. And so we also learned that you could use Cabal or Stack, which uses Cabal underneath the hood, that it can say which packages you want to use. And if the difference between like Cabal and Nix is that with Cabal, frequently the packages that you're going to import are not built. They're not binary packages. They might be unbuilt packages that you have to build when you install them. And so the trouble with using unbuilt packages is that it takes time to build them. So if you could have a system that was already set up with the binary packages that were already compiled for your system using Nix, it might just be that much easier to use them. However, when you're using Cabal, you can have just as much control as you would with Nix or Nix and Cabal, just to make sure that you're getting the right versions of your packages. You might have in your README exactly what library versions you need to have installed, so that the person can install the right dependencies on their own in order to build your packages that depend on other packages. And what Cabal itself really does is it creates this, package.cabal file. And that package name that you have, say if you, can you still see my my terminal? Are you able to see it? Okay, so
can you zoom in one?
Yeah, definitely a couple of times.
Thank you.
Let me just. Okay, so say you were making some new project, and then you went into that new project and you did a Cabal init. It would create some files in that package, and this new package now has an app directory, and in that app directory there's a main.hs. So let me do that again. So in that app directory, you'll see there's a main.hs, there's a change log, which they always encourage you to do, and a new project.cabal, because the name of this directory was new project. It automatically makes your new project.cabal file. And if you edit that new project.cabal file, you'll see that it gives you information about the author, maintainer, and then what the main executable for this package is. So say my package is called new project, and the main initial executable base is the main.hs inside of app. And the way we know it's inside of app is with this hs source dirs. And here the .cabal file tells us we're running on Haskell 2010 with a base of at least greater than 4.14. And so this is great, you know, totally fine. But that's not the way you define a project, right? In order to define a project, you make a cabal.project file, and the cabal.project file will list any of the dependencies that you need, and will list any of the like that you need to pull in from, say, GitHub or Git, some other version control system, and we'll show those files up, and then
Lost audio. Eli.
So we can't hear you, Eli. I don't think I hear us either.
Yeah. I can hear you too.
Yeah, I thought I was the only one.
No. I think that too. No.
how about now?
Yeah.
Now you
you're
can?
good now.
Yeah,
Oh,
we can hear you. Yeah.
did you hear anything of what I said before?
No.
Oh boy.
Not
Oh.
before you switched. Like right when you switched the slide is when the slide prior to this one is when the audio.
Okay. So you covered, you heard about this one?
Yeah.
Yes.
All right. So let's just see if maybe, I have no idea what was going on. So a couple of people were having difficulties building last week. They couldn't get Cabal run to work or Cabal build to work. And I tried to recreate the problem, but I couldn't do it. I tried creating a WSL2 on Windows installation with Ubuntu, And the problem that the person or a couple of people had was that WSL wouldn't let them install packages on Ubuntu. And I couldn't create that problem. So I don't know exactly what the reason was that that scenario happened. But then I thought maybe a solution to this might be to install Nix and edit the nixconf and add in the binary caches array, the list there, and then install the correct packages. And you could look at this website here about which packages you might want to install. And I can help you with that, but you would really want to install GHC and Cabal at least. And I think Cabal is already installed by default when you install Nix anyway. So I think it's probably okay if you just install Nix and then go from there. But I can help whoever needs to try and install Nix if their GHC system with the GHC up or whatever is not installing the right packages. Okay, so oop, I thought that was animated. Oh, maybe it only is animated. Let me try resharing this. You can still hear me, right?
Yeah.
Okay, so let's try. Can you still hear me?
Yes.
Yep.
There you go.
All right. So what are semi-groups? This is going back to 2 weeks ago. We talked a little bit about what they are. They are very sort of generic type classes that are even sort of higher than normal type classes. They have to have this associative binary operation. And does anybody remember what that associative binary operation looks like? So it looks like the less than greater than, which is in our title to our class, right? So, but not all associative binary operations look like this. You might have the plus, or you might have the single plus. Things that are binary associative means that it doesn't matter which side, the left or the right, the item is on, as long as it knows what to do when it's combined with the other one, then it's going to know that it doesn't matter which side it is. So plus is binary associative for sums, and plus was binary associative for attaching or combining a list, or an array of characters, depending on what you're doing. And so if we take a look at what is a monoid was a semigroup that had the semigroup operator, that less than greater than sign defined. And it also had a mempty, which was an identity value. And the identity value for like sum was 0. And the identity value for an empty list was just an empty list, or an empty string, which is the same thing as an empty list, right? And if we take a look at what a monoid is by getting the information about the monoid, then we would see that monoid is a type, and it has this constraint that it should have a semigroup class, and it should have a mempty and mapend. So mapend is that semigroup operator that that less than greater than. And what we do is we'll take a look at what are some monoids. So if we look at a string, a string or list of an array of chars, or list of chars, you might be able to use the semigroup, the operator on those lists of chars, and you would have this Haskell, mapend coffee, mapend is, mapend cool, and you would say, does this produce the same effect as Haskell ++ coffee ++ is ++ cool? And the answer is yes, because ++ is the binary associative operator for mapend for strings or lists, which have the mempty of the empty string or the empty list. And the sum1 mapend sum2 produces the same result as sum1 plus sum2, because the plus operator for sums has that mempty of an empty sum, which is 0. And so if you got the value of an empty sum, you would get 0. So sum1 plus sum2 is the answer sum3. And if you got the value from inside the sum, there's a function called getSum available on some types that would allow you to get the, say, numeric value of what that sum was. And so one thing that we also found was that you could take a foldable and a foldable with some monoids, so a foldable of some monoids, and you could use this fold function, this fold operation on that foldable of monoids. So imagine whenever you see the word foldable, think list, but it could also be maybe, it could be whatever falls into that foldable type. And then you could take those foldables and fold them, and you could get a result that was of that monoid type. So if you said fold the list of the strings Haskell and coffee, you would get Haskell coffee. And if you did fold just Haskell, nothing, just coffee, so maybes are monoids, then you also get this just Haskell coffee, the mempty of a monoid, the mempty of a maybe is nothing, right? And so it's the empty string when you're dealing with folding strings. And so here we see that we've turned that Haskell coffee into a maybe itself using that fold with an array, with a list of maybe types that are inside of them. So that could be helpful. So say you have, say you got a bunch of maybes and you want to combine all the values of those maybes, but you don't know how to do it. You might have, let's see, oops. You can still hear me, right? As I switch here to this new project.
Yeah, you're good.
Okay. So you might have import data foldable. You might have fold just some 3. Oops. And you can't do it. Oops. I think we need. No, okay, you can't do it. because the type, the inside the list has to be something that is a monoid, which means that it's inside of a foldable, the array, and it is a monoid. And just sum was not a monoid, but just a string, just maybe string was a monoid. Okay. And so you might have get sum. So I said get sum was a function that exists on the sum. And remember, if you fold sum and sum and sum and sum, you would get some value, a sum that had a sum of whatever the values were inside of it. So say you had these sums, what do you think you would get as the result here for the get sum of the fold of this foldable here? Anybody have an idea? Let's see.
It's sum 42.
42. Okay, so you on the right hand side of that $sign, you would get sum 42. But if we use the get sum, what we would get out of it, would be 42. So get sum gets the numeric value inside of a sum constructor, constructed type. So fold sum1, sum2, or sum1, sum30, blah, blah, blah. This fold would be sum of 42, and the get sum of the sum would be 42. So yes. Okay. All right, so imagine you had a database of the Coffea Arabica bourbon cultivars. So we have this coffee list, or this coffee database, or we're going to call it the cultivars database. And it's a list of tuples, right? And the tuples are integer, comma, whatever the name of the type of cultivar are. And so there's a lot of cultivars I've never heard of. And there are some cultivars I have heard of. But the interesting thing is these are all sort of mutations that weren't necessarily human. They were human created, but not on purpose. They were accidental mutations, right? But things that people still cultivate now because of their mutations that happened. And so say you were going to some coffee shop that had only cultivars of this bourbon type of Coffea Arabica. And they only used a database. So say you had to pick a number and it would speak out loud what your choice was. So say you said, I had to pick 0 in order to get the bourbon Poitou Laurina. And you had to pick 1 to get the SL28. I don't know what happened to my 10th item on there. I thought I had one more item on there. So it goes 0 through 9. So 10 items in the cultivars. And so say we wanted to look up the, that should be 4th and 11th coffees. You might want to use something that does a lookup and gives you a value out that is the item at 4 or 3, because that would be the 4th item, right? Or 11, which doesn't exist on the list. And so you would expect if you gave it, if you looked up the 4th item, you would get that tekisik. And if you looked up like the 11th item, then, or 12th item, then you would not get anything, right? You would get nothing. And so what type of thing do you think this lookup returns? Anybody have an idea? How about a maybe, right? So we have this lookup where some A is tested for equality for that first value in the tuple. And if it matches, if A matches A, then we return maybe B. So if A doesn't match anything, we would get what is the absence of a maybe? It's the nothing. And if we got a value for A, then that would be the maybe B. So what is maybe B? It's just B if it exists, or nothing if it doesn't exist, right? So if we did look up 3 cultivars, so if we went back to this list, if we looked up 3, we would get tekisik out. It would be just tekisik. And if we did look up 10 cultivars, so does 10 exist on here? No. Then we would get nothing. But you say, but say you were this customer at this cafe that only had the ability for you to pick a number, but it had to say it out loud for the person behind the counter to know which coffee it was. So you pick a number from a display and it says, okay, we got to look up that number and then say out loud what that is you're ordering. So you'd say, I'd like a cup of number 3. And you'd want the computer to say, I'd like a cup of tekisik, right? And so how would you do that? You would think, okay, I'd like to combine this, I'd like a cup of, and the result of that system looking up number 3, right? And so if you tried to do something like, I'd like a cup of plus, so adding on a string to the lookup result, what do you think you get? Oops, I'm letting you cheat right here. So you would get an error, and I don't know why I can't see the chat when I do this. Oh well. Let me see if I can open chat and put it on this screen. Okay. So you would get this error, and the error would say, hey, you've got this char type, this array of char, or this list of chars on the left-hand side of this plus, and in order to use the plus, you need an array of chars on the right-hand side. However, what you actually got was a maybe string. So it says the second argument of the plus is not correct. So how do you handle that? I mean, seems like there might be a couple of ways to do this. One, you might do what we were thinking of before. You might do fold let's see, just, I'd like, oh wait, let me load the, oh wait, which directory am I in? Okay. Say you want to see fold just I'd like a cup of, you could do this just oh sorry, look up and then 3 of cultivars. Hey, and it works. Well, sort of with a space. We'd add in a space. All right. I'd like a cup of tikisik. That works. That gives you this just out. But you would need to know what this array, this list was beforehand. Whereas maybe what you want is some other way of getting this value together. And so how do we do that? You can't have the plus string and a maybe, so why not make a function to process the string and maybe string and make a maybe string out of it, like we just did with the fold, but making a function that makes it, you know, just addable into some other function where we get out the value. So we have this map to maybe idea that takes a function that applies a string to a string, and the function that we're applying a string to a string of is actually this function here, and it's going to be a well, we'll talk a little more about it, but it's the I'd like a cup of string plus plus, and we're applying that to something that has a first argument that's a maybe string. And so the thing we're applying it to, if we look back here, is this look up 3 cultivars. And so then we would say, okay, if we gave it a first argument that was a maybe string like the lookup, we would want to get out a maybe string from the whole calculation, right? So we have this overloaded definition here of map to maybe, where the function coming in, which is this string to string function, is applied to nothing. And if you try and apply a I'd like a cup of to a lookup that gives you absolutely nothing, then you don't really want a cup of anything, right? So you would return nothing for that one. But say you had a function that was being applied to just string, and so string here with the lowercase s is just the name of a variable, right? So it's just meaning that something came back from that lookup, and so in that parentheses, we're sort of destructuring, you might say, that condition where instead of nothing, we get a maybe that has a just value. And then we return a just, so another maybe. And then we're applying this function that takes a string and returns a string. So if this just, it means that there's a string there, then we're applying this function to that string. So we'd be applying function, which is the I'd like a cup of plus plus, to the string result if there was a just value in the lookup 3 cultivars. So we would use it like this, map to maybe I'd like a cup of plus plus, right? Look up 3 cultivars. And you might say, okay, Does this work? Yes, yes, it works. If we look here, if we do map to maybe of I'd like a cup of and plus and look up 3 cultivars. We get here just I'd like a cup of Takisik, just like we got here with the fold. But here we've got this map to maybe. Here we had to use that original structure of the list, whereas here we're just not introducing any new data structure. We're not introducing any list here. We're just applying a function to that lookup result. And so if we look into this, so that thing in the parentheses is a function, right? But why do we call it a function? Can anybody figure out why we call it a function? Anybody? So what's another way that we could write that first parentheses item? Anybody have an idea?
With some?
You can't use sum because it's not a number. But we talked about yeah, so Roberto says the plus operates on the string. Yeah, it operates on 2 strings. Remember, it is a binary, or it is a binary associative function. So the plus is actually a function that operates on what, 2 strings, or 2 lists, or 2 things of the same type that have that constructor that has the, or that defines that plus. So if we look back here, one other way to write that function, if we go back up here, this is something that Haskell allows you to do. So we might write an arrow function, a lambda function here, that writes this function like this. So this is a complete function, but this is what we call, a partially applied function. So this says, okay, take this, start operating on this, and if there's a result on the right-hand side, then apply it to this function. So this says, we're partially applying this function, we just expect one more argument, and we don't know what that argument is yet because we have to evaluate whatever result comes out of the lookup here if there's a just value of the maybe, right? So if this returns just Takisik, then we would have an argument on the right-hand side of this plus, because inside the map to maybe, the left-hand side, or the right-hand side of whatever you're passing into this partially applied function is string, right? So you're applying to this function, I'd like a cup of plus this string. And so that's fully applying that function. So we can write it this way, or we can write it fully applied, but unevaluated. like this. So this also works. So this also says, just I'd like a cup of tikisik. So this is the same thing, but with a fully applied function, lambda function, rather than a partially applied lambda function like this. Does everybody get that? Okay, yeah, the plus plus is the concat. All right. All right. So, what is the meaning of this map to maybe, right? So it takes a function and a maybe, and then unwraps the maybe if it exists, and makes both types of conditions into a maybe again. It's a function that takes two types, strings and maybes, converts them into another type, which is just strings, but then returns the third type, which is actually the second type here, a maybe. So, right, the third type, the return type, is a maybe, and the second type is also the same type. So both the second type and the third type are the same. And so what you're doing is you're converting types, right? You're making it so that you can apply something to two things that are initially different types, but because of applying this map to maybe, you're able to join the two into one type. And so you can only do this on things where you can apply something to the innards of two different types, or the unwrapped types, or something like that. So you can only do that in some conditions, and the only problem is, in this map to maybe, we say it in the name, we can only map strings and maybes to maybe string, strings and maybe strings to maybe strings. It's pretty restricted, constrained, right? It's constrained to maybe strings, not just maybes, maybe strings, right? And you might want to make a more general map, like this, a general map, which goes from A to B, that takes some f of A and returns some f of B. And this is a powerful type definition, right? This would say, if you had some A and some B, and you could provide a function that transforms A to B, say you were transforming strings into numbers, and if you had some something that returned a maybe A, which is maybe a string, and you could combine this this function of that applied to that A, which is a string, then you could return out a type of a B. So here F was maybe, here F was maybe, right? And the A and B were both strings. And so what kinds of types will work for this type of function definition? You might say, well, let's look at what kind of type a maybe is. And maybe is a star to star. And what does that mean? It's a constructor. It's a type class that is a constructor that takes one argument and returns some star. So if you had a maybe string, so if you did maybe string with a kind of maybe string, you might get out kind. Here, let me move this up on the page. You might have kind maybe, and that gives you the star to star. But if you fill in one of those stars, say if you did a kind maybe string, you'd get a maybe string has a type, has a kind star. And what other types of things have a kind star? Let's say bool. That has a kind star. So a bool, you can't apply. The bool constructor isn't really a constructor, right? But a maybe string would be like just 5, right? This is a maybe string, right? But if you did true and you looked at the type, that is a bool. But if you looked at just 5 and you looked at the type, this is a maybe string or a maybe char array, right? But if you did type of just, it would say this is a maybe A. We don't know what A is because just is a constructor of the maybe type, right? And if we did just nothing, it's also a maybe A, but it doesn't take the A to inform us that a nothing is of a particular type, a nothing is of a general type maybe. But when you're applying it to or giving it in a situation that has a maybe string, that nothing string doesn't work because nothing isn't a constructor. Nothing is just nothing, right? And so if we go back here, so we have this maybe that takes that is a type constructor that takes another type and then produces a type. So if it takes maybe string, the type that's resulting is a maybe string, is something that is of maybe string. And if you look at kind either, we've talked about either before. Either is a little bit different. Either is a star to star to star, which means if you did kind either string, what do you think it would look like? Anybody have an idea? Yep. So it would look like either string that is of type star to star, which is just like the maybe type up here. So the star to star, and if we wanted to create a map to either, which is slightly more complex, you would say you sum map to either with a function that goes from A to B, where you have some either, say left is a string or nothing or whatever, and you have this function where if the left value, whatever left is, we don't know what left is. So this left up here is not a type of anything that we know. We just know that we would return it if we got that left value out of either. Whereas if that left thing was was nothing, then and we had a right value, then we would get the right value and we would apply that right, or we would return the right function, a right construction of whatever that function was applied to the right value. And so this is like way out there for a second, right? It's a little confusing. So maybe we wouldn't necessarily need this, but you might say, if you map to either, that gave some, oh, yeah, we'll take a little getting used to, yes. If you had this function that said X and you're applying, I'd like a cup of plus plus X, you know, or I'd like a cup of plus plus, and you applied that to something that evaluated to write X coffee, you would get the right X coffee, and the function applying I'd like a cup of into whatever that right value is, which is X coffee. So right X coffee is actually taking an either that we haven't defined yet and making it either left, which is some type that we don't really care about, and string as the right hand value. So if we do that, what do we get here? Let's do map to either. So we say I'd like a cup of, and then we would say write Tekisik, right? So we got this. We would assume we return a write of I'd like a cup of Tekisik. So that does the same sort of thing. But wouldn't you not be surprised, like we had with the fold, where we created a function for fold, that there was already something inside Haskell that did this for you? And what do you think this is called? This is called a functor, and it's applying whatever you're doing to something that is of a particular type. And so it's taking your two types. So either you've got a maybe this or string this and a maybe string this, or a string this and a left something else, or a right string, and combining them, and then folding them or mapping them into the same type as the thing on that you're applying it to. So they call this a functor, and the way you can do this is with something called fmap. So fmap says I'd like a cup of Tekisik. I think you can also do, oh, wait, no, I can't remember what it is right now. We'll look that up in a second. But if you do the fmap instead of map to either, or instead of map to maybe, then you'll get the same result. So if we did map to maybe, might actually, I can't remember. Here, we'll look up. So this type here, fmap, or the information is it goes from A to B and makes applies f of A, and then whatever that function is applies that and returns that f of B. So if we look at what the type of fmap is, it is that functor f. So if we do, oh wait, I think I need to import something. Hold on. I think we need to import. Hmm. Do we need to import data functor? Hmm. I thought it was this. I have to look this up. Okay, so I'll look that up later. But the fmap is the thing that is the functor that says apply this to this in change the type of both to whatever the second type is. All right. So I'll let you talk for a couple of seconds while I remind myself how to apply that fmap type simplifier. One of the other things you might notice is that if you have fmap, why do you need map? Because can't you just take fmap and apply it to like a list, and since its type is, you know, very generic, can't you just apply it in place of a map? And the truth is, yes, you can apply it in place of a map. You can say, hold on. Let me see. But let's see. Why isn't this working? I think it might need a full function. Yeah, so let me share this. Oh, my dumb. I don't know why I was using question mark. I should have been using $sign. That's what I was wrong. Okay, so you might have some function that's partially applied, like 3 star, and you have this fmap operator, or you write fmap whatever that partial function is, followed by some list or foldable or mappable item. And so we might do, I'd like a cup of coffee plus plus, just coffee 1. So it's I'd like a cup of coffee 1, whereas you could also do in place of that with the infix operator for fmap, the less than $sign greater than. So you'd combine whatever this function was, apply this function to this maybe, but unwrapping what's inside the maybe, if you can apply this function to what's inside of that type. So this is that functor operator here. That's basically like a map, but you're mapping a function onto a type that you can do something with the innards of whatever that type is. So if we had that 3 multiplied, and you had this list here of 1, 2, 3, 4, what you're doing is you're applying to some list type of numbers something that internal. So remember, this list is of a list of nums, and this 3 is something that you can apply to a num, right? So this list is that f. So if we look back at our general map here, that f of a is a list of a, so a foldable of type A. And we take a, which is, say, a num, and we return a b, which is, okay, also a num, and then we return a list of that b, which is the num that we were applying. So if we have here 3 times 1, 2, 3, 4, 1 is a num, so 3 times 1, and then the second value would be 3 times 2. So this is the same thing as applying a map, right? So if we do map 3 times, it's the same thing as fmap, right? So why do we need map? We don't, but for fmap to work, it needs to be something that has the instance of the functor type. And what has functor? Lots of things have functor. IO may be anything. Basically tuples, lists, ethers, and if you look at if you import data, maybe I think if you do, I have functor somewhere, there's a maybe that's defined. Oh, there. Oh, it was already defined. Never mind. Lots of things are in that class of functor, or instances of functor and you just have to import the right library, import the right module, whatever, and then you'll get access to that being used as a functor. And you'll see this a lot. You'll see the functor application in a lot of things where, say, you're logging out some information. So in the Plutus application backend, we use it a lot when we're logging out something and we need the resulting type to be the combination of two different types of variable, elements. So say it's a string IO and byte string or something like that, and you want to convert it all to a byte string. Unfortunately, you end up converting things to byte strings where you would much rather convert things to regular strings. But there are limitations to what types will work. And you sort of destructure things into other types later, but basically that's what happens. So let's take a minute and see if you guys have any questions, and then we'll break out and have you guys play around with the FMAP and its application. So let me go back here. I guess we don't need to really go into breakout, but we'll do two person breakout rooms. I think looks good. Anybody have any questions first? What is the difference between FMAP and MAP? The signatures. If you look at here, let me share again. If you look at the type of map, it's A to B, right? It's that same way that FMAP starts out, but the F of A and the F of B are constrained to list types. So whereas if you look at FMAP, the only thing F has to be is a functor. So a list is in that instance of functor, but F can be anything. It can be maybe, it can be either, it can be list, it can be whatever. It just has to be constrained to that functor type, whereas map is sort of like a simplified version of FMAP that you can use only on lists. And why would you care whether you're using map or FMAP? You really don't care, but if you're trying to make sure that you're using the right types, you may want to use map instead of FMAP to make sure that you're only operating your FMAP, or you're only operating your map on lists, and that you're expecting a list to come out of it. Does that sort of make sense? So FMAP is more robust. Yes, FMAP is more robust. It is less constrained than map. It does more things. It can operate on more types. It can operate even on IO types. So like you might have the FMAP of one IO type onto another IO type, which is like way out there. And so yeah, it is. Yeah, so there's this less than $, which is the partial derivation of the less than $, greater than, which is, I believe you can't use, so the less than $, if I can't remember how you get the type of that. Anyway, but the less than $ is the partial version of fmap that is used to define what fmap actually is. So if you notice that A is when there's no other type, right? That then it's backwards, right? There's no you might have some f of b and some a, and you just return an f of a. So you can use it by itself. However, I believe I've never seen it actually used with just the less than and then the $, but I'm sure it is. I'm sure there's a way to use it. Anyway, but I've seen fmap written out, and I've seen the less than $, greater than. Okay. So let's play around with that. I'll make some breakout rooms. Okay, Sebastian, have fun. Hey, Jaime, how are you doing? Oh, I can't hear you. Let me see. Is that my sound or your sound?
It's my sound. It's my sound.
Okay. You doing okay?
Yeah. I'm trying to understand everything that you said, because it's my first time interacting with Haskell,
Yes.
and everything is new for me. But some structures are similar, like the currently programmation of object orients
There
from
are some
structure
things, right? Yeah, like map is something, although there's no like fmap. There's no corollary in like JavaScript, but there is a map, right? There's map you can use to map over an array, but there's no like abstract definition of types that lets you say, well, I'm going to map over a dictionary because that's what you can do, or something like that. You can't do it. Whereas in Haskell, as long as that type is part of that functor type class, then you get to explore the whatever you can do with that type, whatever people have set up for you to be able to do, or if you implement some more, you can add to the instantiation of that class's implementation of the functor in order to do more things with a type. So say you had that database type, that dictionary type, which was just a list of number, comma, whatever. You could create an instance of the functor for that particular type if you called it a data type, and then instantiated functor on it, and then applied something to that class. You could totally do it, and it would be totally different from anything anyone else had ever done before that. Yeah.
And learning to interact with the LCI, because everything of Haskell, like it is new for me. The compilers, the packages, the dependencies, everything is new.
Yeah, and I don't program that much with Haskell because we have more advanced Haskell and Plutus developers on our team than me. I'm more like overseeing the development than I am actually developing. And so even when I get in these situations like I did before, like I couldn't remember what the constructor type was, then you know, you learn, you search, you find it, you get used to it.
I have to do my own research
Yeah.
to learn more faster, because I am an SPO, yeah, and my main job is to ensure that the pool is working
Right.
fine and is up and running.
Right.
But we want to learn Plutus, Marlowe, Haskell to understand the environment of Cardano
Right.
in the development environment.
You're not alone, right? A lot of people want to. And so that list I gave of Lars's class on Haskell in Mongolia is a good class also to go through, especially since it deals with mostly things that are related to Plutus. And it doesn't go into Marlowe because Marlowe hadn't been invented yet, but it goes into some stuff about like how you would use either in a situation dealing with some contract or something like that. So you might see the things you're already familiar with now in there. Okay, I'm gonna go check on other groups. I think your group mate left, so I'm gonna move you into a different group.
Okay, cool. Thank you.
Hello. Any problem? Oh,
Roberto, I just shared something with you via DM. You can try that.
Thank you. I will. We got to keep that over. All right. Thanks, Ozoma.
So you can share your screen again so that we'll see it if it works.
you don't have to share screen. I can stop recording too. I'll stop recording. Hold on. Here, I'll pause.